Imagine waking up and discovering your room isn't what it seems. The lamp, the carpet, the tiny crack in the plaster, they're all images produced by a more economical script, a pattern written somewhere else. What if the three-dimensional world we trust is actually an emergent projection of information encoded on a distant boundary? That bold, beautiful claim is the holographic principle, and it insists on nothing less than a reimagining of space, time, and what it means to be real. Let me take you through it, slowly, then faster, until the ordinary feels like an illusion worth investigating. Start with a glass of water. One way to describe it is exhaustively. Every molecule, every velocity, every tiny interaction. That's information heavy. Another way is to describe just the surface. Temperature, ripples, how light plays on it. Sometimes the surface description, surprisingly, contains enough information to predict what the whole glass will do. That strange economy, where the boundary carries the bookkeeping for the interior, is the whisper that becomes the holographic shout. Black holes gave physicists the first, unmistakable clue. In the 1970s, researchers discovered that black holes possess entropy, a count of their internal information. Wildly, that entropy scales not with volume, but with area. The information capacity of a black hole is proportional to the area of its event horizon, not the space inside. It's as if the interior's instructions are stamped on the surface like a barcode. If a maximum amount of information that can be stored in a region scales with its boundary area, it suggests a mind-bending possibility. Perhaps what we call volume is a derived description, constructed from data on a lower dimensional boundary. That's the germ of the holographic principle. To see how this idea blooms into rigorous math, I meet ADS SCFT, a conjecture from Juan Maldacena in the late 1990s. In certain idealized universes, those with a specific negative curvature, a gravitational theory living in a volume, the bulk, exactly matches a quantum field theory without gravity living on the lower dimensional edge, the boundary. Two different descriptions, two different languages, but they write the exact same story. If you accept this duality in those settings, gravity and spacetime aren't fundamental. They're emergent from quantum information painted on a boundary. Suddenly, the hologram metaphor is more than poetry. It's a precise mathematical tool. Let's make the intuition visceral. We think of space as a backdrop where stuff happens. The holographic viewpoint flips this. Space emerges from relationships, quantum entanglement between bits, rather than existing beforehand. Picture a cosmic web of quantum bits. Each link in that web is entanglement. The pattern and strength of those links could be what sculpts geometry. Areas and volumes become counts of entangled connections. Tear at the entanglement and the geometry shifts. Gravity, in this picture, becomes an emergent phenomenon, a macroscopic effect of microscopic information dynamics, perhaps akin to a thermodynamic force arising from entropy bookkeeping. This is not just abstract theorizing. Holographic dualities have teeth. They give physicists practical ways to calculate properties of strongly interacting systems that would otherwise be intractable. Condensed matter researchers use holographic ideas to study unconventional superconductors. Nuclear physicists use them to probe quark-gluon plasmas. Even if our universe isn't literally a projection, the holographic framework works as a computational microscope, revealing behaviors and offering solutions where traditional methods stall the holographic. Perspective also softens a major crisis in theoretical physics, the black hole information paradox. If black holes evaporate and information vanishes, quantum mechanics, which insists on unitarity, is violated. But if information about objects swallowed by a black hole is stored on its horizon and later imprinted subtly in the emitted radiation, information need not be lost. Recent advances, entanglement islands, replica tricks, and entanglement wedges, use holographic insight to show, in simplified models, how information can indeed be preserved. The paradox isn't solved for all realistic scenarios yet, but the holographic way of thinking has been essential in mapping a plausible path to unitarity. Now, imagine your own brain. The retina is a nearly flat sheet of photoreceptors, but your experience is rich, three-dimensional. Your brain reconstructs space from two-dimensional patterns of light. The holographic principle suggests the universe might be doing something similar on a cosmic scale, a lower dimensional ledger of quantum data being interpreted, by the rules of quantum mechanics and gravity, into the 3D plus time tapestry we inhabit. You aren't a hallucination. You're an emergent pattern that persists across descriptions. If the boundary description and the emergent bulk description make identical predictions for experiments, the emergent world has all the functional reality we care about. There are limits and caveats. The precise ADS-CFT dualities are best understood in special spacetimes, not the exact geometry of our observed universe. Extending the holographic logic to universes like ours is an active and speculative frontier. But theoretical physics proceeds by following mathematical breadcrumbs. The black hole area-entropy relation, the success of ADS-CFT in particular domains, and the recent progress in understanding information flow in quantum gravity together make the holographic hypothesis too compelling to ignore. The implications ripple outward, both practical and philosophical. If information is the true currency of reality, then physical laws become rules for information processing and transformation. Entanglement becomes geometry, locality. The idea that things only influence nearby things might be emergent rather than fundamental. In that case, distance is an emergent label describing weakly entangled regions. Two far-flung regions can be close if their underlying informational geometry connects them strongly. That view recasts quantum weirdness. Non-local correlations aren't spooky exceptions. They're symptoms of a deeper informational structure. For a moment, indulge a thought experiment fit for science fiction. A civilization learns to read and edit the boundary code. By altering the ledger, they subtly change the emergent interior. A weather pattern shifts, a mountain appears, a life is saved. Reprogramming reality becomes information engineering. That scenario raises urgent moral questions. Who has access to the code? How do you prevent catastrophic bugs? While fanciful, the metaphor isn't entirely divorced from our world. Right now, we edit information that reshapes emergent realities. Editing genomes, rewriting algorithms that steer economies. The holographic intuition emphasizes that manipulating information is the lever of causation. Even if the universe turns out not to be a literal projection, the idea has already reshaped how we think about nature. It has guided powerful calculations, suggested new experiments, and inspired a generation of physicists to view information as primary. The holographic principle is both a provocative metaphysical hypothesis and a practical research program. It forces us to ask, are particles and fields the bedrock, or are quantum bits and their relationships more fundamental? Let's return to the small human scale. You touch a doorknob. That touch obeys electromagnetism and material science. The knob resists and rings true. The holographic picture doesn't deny the knob's solidity. It suggests that its solidity arises from deeper, efficient bookkeeping. Both descriptions, the emergent three-dimensional one and the boundary-based informational one, can be true at the same time because they answer different questions. One tells you how to fix the hinge. The other tells you how the hinge could, in principle, be encoded more compactly. So, is the universe just a projection of quantum data? We don't have a final verdict. But black hole thermodynamics, the mathematical precision of ADS-CFT, and recent progress on information in quantum gravity make the hypothesis one of the most exciting ideas in modern physics. Whether literal or partial, the holographic lens stretches our imagination and sharpens our tools. It reframes space as a story told by relationships, gravity as an emergent consequence of entropy, and reality as a multi-layered tapestry woven from information. Picture the universe as a projector humming at the edge of everything. On its film, quantum inscriptions pulse and encode possibilities. When the projector runs, galaxies bloom, storms roll, and consciousness arises to read the projection back, asking who wrote the code and why it chose to dream. That question may be metaphysical, emotional, and scientific all at once, and it is one of the richest directions physics has pointed us in. The hunt for the code is on, and the chase promises to alter not just our equations, but our sense of who we are in the cosmos.